grades to the problems you guys had in your pre-calculus course. I believe section was 3.5, the word problems for exponential functions. So 100% of what we are doing today is going to be that, and then add calculus to it. So we'll start with population. And the exponential model now will pick up letter P for population, and instead of X, we're going to use time, because population changes in time, right? Case of humans, it takes about 9 months to cook up a baby. So we'll have to measure, right, the population in terms of passing time. So the model we are looking at is population at time t is equal to P0 e to the kt, where P is population, P0 is initial population, and then t is time in years. If we are talking about humans, can you talk about bacteria and have t to be in hours or days? The answer is yes. We can have time in any unit. It's just in general, if you're going to talk about deer, rabbits, people, right, we use years. But you can change t to be any value. I mean, any unit of time. All right, so let's talk about the world around us, right? So what I'm going to do is I'm going to jump to the website, which is .gov website, so census.gov, the population clock, which measures the population of United States and the population of the world at the same time. And we can pick up some values to, calculate certain things about the world around us. So on the left, you have United States at about 330 million. And on the right-hand side, you have the world population at about 7.6 billion currently. So we're going to use the world population, and we are going to calculate some things. Now, this website also provides us with the 10 most populous countries since July 1st, 2019. China, India, United States on the third spot, Indonesia with their 1,000 islands. And then number 10, this is interesting, last year Mexico overtook Japan, because Japan is losing people quickly. So these are the countries, top 10 countries. And when you see the world population there, I'm going to go back in time and pick up another data point so that we can calculate. You need 2 data points to calculate the world's population. So what I'm going to do is I'm going to say over here 2019, and I'll put the arrow into 7.6 billion. Right, so I wrote the first data point, 2019, and I put the arrow, just like the arrow for a limit, right? 2019, and arrow pointing to 7.6 billion. Now we're going to go back in the past. We're not going to go far. 1970, let's say. Put another arrow. So 1970 is about 50 years ago, right? It's 49 years ago. So 1970, I want to know the world population in 1970, so we'll ask Google or Bing. World population in 1970. 3.686, so 3.7 billion. population. That's half, right? We doubled the population in the last 49 years.
That's less than that.
Yeah, I mean...
Yeah, people need to calm down.
Calm down.
Oh my God.
All right. So now we have 2 data points, and we can go and do some calculations with these data points. I don't think that the stream is going. I'm not sure if anyone is watching and following, because I see the red dot at the streaming software. So we might not be pushing enough bandwidth for the video. You'll have to watch this either with the other class or one of the older lessons, but they're all different. So I think I did the same example there. So I mean, with the same numbers. Obviously, the numbers from last year are going to be different because population, as you can see, right, changes and adjusts a little bit. So what we are going, we are going to need a scientific calculator for this one, because we will be calculating logs and exponential stuff. So get your abacus ready. If you have the cell phone, you can put the regular calculator and just flip the cell phone sideways. It will give you scientific access to scientific stuff, and even Apple can do it, so it should be okay, no matter what you're rocking. All right, so the first order of business is to set this one as t equals 0 at 1970. So t equals 0 will immediately mean that your initial population is 3.7. So that's our initial population. You can set any year you want as initial population. So we are going to set 1970 as a year 0, which would make 2019, right? That would immediately make 2019 to be t equals 49, right? At 2019, for the population to be 7.6. So this gives you 2 points. The first point is 0, 3.7, and the second point is 49, 7.6. So this is what we have in terms of data points. And now we can use this to come up with exponential model, and you do that in stages. So the first thing you do is once you write p equals p0 e to the kt, you already know what p0 is, because whatever year is set as your initial year, t equals 0, that's what the p0 is. So we immediately know that we can make this equation a little bit better now at 3.7 e to the kt. Okay, we have that. Now, the next line gives us time equals 49 and population equals 7.6. We can calculate k. So this is the first point. And now we go 7.6 equals 3.7 e to the k times 49. Second point. And as you can see, everything is known in this second point other than the value k. So what is this value k for population? Well, in this terrible model, and we'll see why it's terrible, in this terrible model, this k mushes all of the components of population in one constant. The birth rate, the death rate, the ratio between sexes, meaning male versus female, because we do need both in order for this to work, right? If you take a look at the situation, if you suppose if k is negative, then the population dwindles, and that k is that. Now in that k you have the wars, and you have the technically, right, texting while driving and a whole bunch of other things. Everything is mushed into that constant k. And we can calculate k. So we are going to divide 7.6 by 3.7. So 7.6 divided by 3.7. And then we are going to keep 4 decimal places. You ignore non-zero ones, because we want to have, we do not want to take a lot of error, right, with us as we calculate. So this is going to be 2.05405. You see that these are 4 non-zero decimal places over there. Equal to, leave some space, E49K. So what you see now is the exponential equation, which we deal with by using the ln on both sides. We apply ln to both sides. So you will put ln here and ln here, and this ln will kill the e. And ln of 2 point, whatever value here is, we can calculate, so push ln. And then second answer to bring in the numbers, you don't have to type it. Remember, 4 decimals, so we have 0.7198 is equal to 49k, from where we can calculate k, divide this number by 49, as 0.01469. There we go. So we were able to calculate k from the second point. So the first point, when time is equal to 0, will immediately give us the initial population. And then if you use the second point, right, with the 49 and 7.6 billion, which is the current state of affairs, we are able to calculate k. And this gets us to write the exponential model for population. So population, which depends on time t in years, is going to be 3.7 e to the 0.01469 t. So this is known as exponential model. And at this point, we are able to do calculus, right? So far, all of this that we did was a pre-calculus problem that you can find in your pre-calculus homework when they give you 2 data points for population, and then you go and you figure out the equation. Now, this is where Calc 2 begins. Yes?
Can you change the 3.7, like would K work for any initial?
Yes, you can. Yes, you can go as far back as you want. Right? There are people that say that 5,000 years ago there were 2 people there. Right? So you can go. Okay, let's see how that. Anyway, so you can go and pick literally any year you want. Ask Google the population of that year. Set that as t equals 0, and then the difference to this year. K will change, right? Because the model needs to adjust to kind of squeeze through those 2 points. All right, cool. So now we have this one, and I want to know what kind of a calculus I can do on this. And the first thing, obviously, is the first concept we learn in calculus, which is limit. And we would like to see what happens if we are to wait forever. Right, what would be the population of the planet Earth if we send time to infinity? And that will be of 3.7 e to the 0.01469 t. Well, you get the infinity, right? Because you can take a look at any exponential graph, right? And then when you take a look at any exponential graph, if you go to positive infinity, you will go to positive infinity as the y. value. We know that limits calculate y values of function. Therefore, it will go to positive infinity. And this is where we see that this model is not that great. And the reason why it's not that great is because the planet has a finite surface area, right? Yes, it's big. Well, it's big in comparison to this room, but it's actually not that big. Consider that, consider the sun, for instance, the size. So when you take a look at the planet, I mean, it still has a finite surface area, right? And because it has a finite surface area, you cannot fit infinite population of anything. You can't even fit the infinite population of bacteria, right? And bacteria, you can't even see how small it is. I mean, you can see it on the microscope, but yeah. So you can't fit anything infinite on a finite surface. So we see that this model is not good in terms of that. It's good on a short run, right? If you're gonna look a little bit, 50 years back, 50 years ahead, sure, you can do some cool approximations with it, but you can't really compute, right, far ahead. And now, in the light of being able to compute a little bit ahead and so on, we can use it to try and estimate how much time we have before we get into a real trouble, let's say. Better models are models that would account for a number which is called carrying capacity of the planet. To reach the carrying capacity, then you can't add more people than what you have. And that's what it is. So now let's pick any value. Since scientists can't agree whether it's 10 or 15 or 12.2 or whatever, let's just randomly pick any value between those two numbers. So what are we going to set carrying capacity at? 13 it is. Okay. So let's say that 13 is the max, 13 billion max. So what am I going to do? Well, I'm clearly asking a question: when will the population of Earth reach 13 billion? Now, this is also something that you would ask in pre-calculus, not something that you would ask in calculus, because it's a basic calculation. You stick the 13 for p, and then you just calculate t. So it's very simple. So we have 13 equals to 3.7 e to the 0.01469 t. And then you do the same calculation like for the k. Divide 13 by 3.7. We will get 3.5135. Leave some space to stick ln. So now put the ln on both sides. So now we have ln of the answer, which is 1.2566, 0.01469 t, and now divide by 1.469, and that is going to give me 85.54 years. Now, obviously, it's not going to be down to 2 decimals, so let's just call it t equals 86, right, years, because we want to round it to the nearest year. You can even leave it as 85, because 85 is, a round number in terms of fives at least.
So in 2055.
So my question is, yeah, when? What is 86 years? 86 years since time zero. And time zero was in 1970, right? That's when we set our time zero to be. So, to calculate the year, it would be 1970 plus 86 is equal to 2056. So, if this exponential model is the correct one, if this model is good enough to approximate this kind of thing, the planet population should reach 13 billion in 30 years, right? 36 years, 37 years. So, yeah, that's the exponential growth. Now, whether you're concerned or not, that's going to be up to you. We can use more calculus now and figure out how many people we are adding to the planet each year. And that's done by the derivative. If you find the derivative of exponential model, it will calculate the instantaneous change for the year that you plug in. So a p prime of t would calculate the change of population within a given year. Calculate the change of population within a given year. This means that now we want to find the derivative. Now, those of you remember the formula that the derivative of e to the ax is equal to a e to the ax, and this a in this particular problem is going to be that constant k, which was 0.01 whatever it was. So the model P is 3.7 e to the 146. Okay, so 3.7 e to the 0.01469 t. P prime is going to be 3.7 times 0.01469. That's when a drops down. And then you copy the function as is, 1469t. There we go. And all you need to do is to multiply 3.7 by this decimal, and you will have your derivative in respect to time, right? That's a function as well. So now we're going to multiply 3.7 times 0.01469 and get 0.05435 e to the 0.01469 t. So, is there a year that you are particularly interested in to calculate how many more new people are added to the population in that particular year?
This year.
This year. So 2019 will give us t equals 49. I'll put in parentheses since since 1970, right? And you will now calculate p prime. I'll put 2019 even though we're plugging 49. 0.05435 times e to the 0.01469 times 49. And we can calculate this, right? This is not an equation now. This is just a straight up calculation. You calculate the exponent, raise that, and then times the number. Your TI-83 can, or 4, whatever you have. Can calculate everything in one shot. So 0.01469 times 49, and I'm getting 0.112. What are the units for this? Billion. Very good. So how many is that? Yes, it's 112 million people are added to the world population just this year. That's a third of our population of our country, right? 1/3 of US is added globally, right? To the whole planet. And that this year, clearly, the more people, the faster the rate as we go on, because that's how exponential functions work. Exponential functions, a lot of people don't get it. They say, yeah, but they're working on colony on Mars. Really? If you consider the exponential growth, I mean, come on. People are used to linear thinking, right? And linear and exponential are completely two different animals, right? Consider this. Let's do an interesting exercise to see how doomed we actually are. Hardly. So what we're going to do now is consider, let's say it is a jar over here, right? Or a can or whatever. And you're going to put one bacteria on the bottom.
Oh, just kidding.
Just right there.
I know. I just wanted you to try.
So you put one bacteria on the bottom of this, and let's say it's noon, right? From noon to midnight, bacteria will fill the jar. And you can't fit any more bacteria, right? So my question to you is, at what time it's half full?
So every minute? Or every minute it splits?
Bacteria splits, yeah. Each bacteria will split every minute into 2 bacteria.
How many bacteria does it take to be full?
Don't worry, we don't care. So what was the answer?
A minute before midnight?
Wait,
Excellent.
what?
Mm-hmm.
What did he say? No,
He said at 11:59 p.m. At 11:59 p.m., this jar will be half full. Because what happens at that minute? Yes, when the minute goes to 12, every bacteria in the bottom half will split in half and fill out the other half. So now,
Yeah.